because everybody's waiting for the lunch. But still, thanks for coming for my presentation. And yeah, well, to begin with, let me kind of introduce myself, and thanks for having me here in Kiev. I'm Maciek Próchniak, and I work in a small, not so small, software development house in Warsaw. And well, my background is that I'm an algebraic topologist, if you know what it means. so some time ago I used to deal with group homology, monads, Haskell, and topologiczne prostranstwa. Yeah, that's what it's all about. But for last, I don't know, 5-6 years, I've been dabbling in talk with ML, GW2, SGI, and more or less trendy abbreviations. Yeah, but I think that from my mathematical times, my sweet spot is still this functional programming. Well, that includes Scala and a bit Haskell. So what I'm going to talk about today is, of course, how to prevent bugs, right? Because most of the talks at these conferences are about preventing bugs. So how do you do this? First, you write tests, right? If you were at my friend Pavel's speech yesterday, you know how to do it with how is it called, SRJ and other stuff. But if that's not enough, what do? You do defensive programming. That's also a good point for making tests. You write, if something is null, then throw a assertion error, and then you have the code later with that. And then you write more tests for your defensive programming clauses. And then, well, if you're really hippie, you can write contracts using some libraries like Próchniak and stuff like that. And then you write tests for them. And so on and so on. And you know what? It works. It works. I mean, I'm not so good in TDD and stuff, but I believe people who do it. But what you end up with is something that I kind of call guerrilla defensive programming. It looks like this. I guess you know what I'm more or less talking about. Your code is littered with barricades so that all your bugs can't pass. And yeah, guerrilla warfare is quite effective, I believe. But the city doesn't look good. And I believe that our code, when it's littered with all these defensive programming clauses, also could look slightly better. So we're going to look at the possibility to do it our way. To do it with static types and compiler. So this is a quote from some random blog about Scala and stuff. And it says like, having static types is all about preventing bugs by allowing uber smart compiler. This is important part, right? Our compiler has to be uber smart to humiliate you on a regular basis. Just as you do with tests, right? Your tests are humiliating you. You're red, and then green. Yeah, you're not humiliated anymore. But then compiler will humiliate. And that's all. And the compiler will make sure you're doing the right thing before it's too late. And before it's too late is like really early, like with unit tests you have really short feedback loop, but now we want something better, right? We don't have to we don't want to hit this magic combination like Control Shift F9 or 10. I don't remember how it's going in IntelliJ. We have to have our feedback faster. Okay, so because we need uber smart compiler, I chose Scala mostly because from time to time I write in this language. So just a quick question: how many of you know Scala? Yeah, more. So probably if some part of this talk won't be much of interest for you, especially if you do it on a daily basis. But hopefully some parts know. Yeah, this is the author's blog, if you want. And this is another quote that's kind of on different side. Some time ago I read or watched a presentation about how dynamic typing is superior to static typing, and the author, who was some hardcore Pythonist or something like that, said like in his code base only 1% of issues in Python system are type errors, attribute errors, and name errors. And the conclusion was that you don't need static typing if only 1% of your bugs are those that can be avoided by having compiler. And at first I think, well, maybe my talk doesn't make sense. That was kind of hard moment because it was like 1 month ago, and I was really already scheduled here. But then, the more I thought about it, the more I realized that it's not about those bugs, like type errors not implemented and so on. It's about such errors like null pointer exception, like uncaught IO exception, because, well, you cannot avoid IO exceptions, just like that. And also exceptions like error out of bounds exception, item not found, and some crazy constraint validation exception. So this is what we are going to talk about, because if you use dynamic programming like Ruby or Python or, well, heavens forbid, JavaScript, you just even cannot think that you can avoid such bugs and errors by using compiler. But we'll do it, or at least we'll try it, and we'll build some static type stronghold, so that all those strings and nulls and other bugs will not come inside. That means we have to have good defense outside, right? If somebody gets inside, then he's safe. There are no barricades. Our code is free of defensive programming barricades. But on the outside, we have to have some good defense, lines of defense. And how do they look like? Like first, we have some main servlet or whatever, the top layer of our program. Then we should have some I/O that is highly dangerous. Then we have arguments parsing, because in fact all arguments for our programs are strings, right? Either it's command line and main, either it's parameters from HTTP requests. So here, these are our main lines of defense. Then we have some validation logic, then business logic. These are our business logic rules. We want to feel safe there, right? We want to have good contracts once we get this deep. And then we have collections, users, and so on. So if you look at this stack, you may think that it's kind of different than normal free-layered architecture or something like that you have, web, logic, and at the bottom, in fact, you have I/O, right? Access to database and so on. This is more common with kind of hexagonal architecture. That hexagonal architecture. That you have world outside. You can communicate through some ports, and it's either with web via some HTTP requests, or it's with database. And inside your hexagon, you have your business logic that doesn't need to communicate directly with outside world. So where do we start? We start with something really, really simple. In normal Java, you usually write something like this. I have some user ID, I have some method for getting user, and somewhere in my code, I do this. I cannot think how many times I did this, right? So, of course, this is clearly wrong, apart from the fact that this should be large L. But that's not what I meant. Yeah, this is, for me, that was a source of many, many bugs. And why is it so? Because, well, the signature of method in Java just takes object, right? And because it's Java, it's backwards compatible, probably it will be the same for the rest of the days. In Scala we can do slightly better when we use appropriate libraries. Well, this is normal Scala code, right? We have user ID, it's more or less the same. Then we have some magic import that I'll probably talk about sometime later. And we have this clause. Yeah, this looks like JavaScript, but it's not referential equality like in JavaScript. What's interesting is that this code won't compile. Like here, I've got one. So this is the semi-Java code, and yeah, IntelliJ warns me that it won't compile, but still, I'm comparing strings, so it works. But here, if I uncomment this, and I'll hit make, yeah, even the IntelliJ tells me that it won't compile. So it's it's really simple method, right? Just type safe equals, but it can save us quite a lot of work. In fact, it's kind of more elaborate. We don't have to time. Probably I will post my repository on GitHub, because this equality method can use something like implicit parameters. For those of you who don't know Scala, it's like having comparable pass to compare to method, but with some more or less default values. So okay, that was the first easiest example. And then there are many types of bugs that come from bad naming. The first thing that I usually encounter is this. This is, for me, it's the crux of bad naming and bad types in Java. Like, each time I write such code, I wonder, what does it really mean? Is balance greater than price? Or price greater than balance? Yeah, I guess some simple enumeration would suffice here. But there are also other points to make. Like, for example, take this method. Like normal Java method, if you are a follower of Uncle Bob's clean code and so on, you know this is bad. This is bad naming. You should do something else, like this. Like in dynamic languages, probably in Ruby or something like that, you won't write type. You'll write descriptive name. But in Java, we can do kind of better, right? We can use type to know that statically it's double, and then we'll name the argument so we know it's positive. But can we do better? Can we make a type that will represent positive double? It turns out it's of course it's possible with all the valid classes, but in Scala we can do slightly better. We can tag type to make it contain some metadata. In Java, you can also do so, right? We have annotations for nullable, email, and so on and so on. And then you plug in some JavaX validation mechanism, and then your field will be validated. But soon enough, your code looks like this. This is the code from my current project. It doesn't look too good. Like, for those of you who search where is the method definitions, here and here, right? And this is metadata. Well, maybe I shouldn't bash it too much because it's Swagger and it's quite a good library. But in Scala, we can do something like this. We can tag our type double. This is some overloaded add with our tag. And what will be our tag? It will be trade. For those of you who don't know in Scala, you can think of trade as interface with possibly implementation. But here it's just pure interface or trade. So we can have this tag, that tag, and how do you use it? Well, when we want to have length, we tag our double type with meter. And then we have capacity, we tag the same double value with liters. And then, lo and behold, this is the type. It's double tagged with meter. Its capacity is double tagged with liter. Below, I won't show you what this method does. Again, it's from Scalaz or Shapeless. I'll talk about it later, but it does some heavy lifting, and some people say it's kind of, miracle that it works. But it works. And the most interesting thing is that inside it's still real double. We can do plus, thin, or whatever. We get double. We lose the tag, but it's not any value object. Just normal double with tag. So I think it's quite interesting thing. But sometimes it doesn't suffice. And then you usually use old stuff like which was invented by Martin Fowler like probably 15 years ago, like with value classes, money, and his seminal work on enterprise architecture patterns. I don't know I can't remember the name of the book. But in Java, it looks more or less like this. This is what it takes in Java to have real good value class, right? With Haskell, equals, and so on. I must say that once I showed this talk, and people would point me, hey, in this line you have error. Yeah, that was quite fascinating. And in Scala we can do we can do it much easier, right? With new version of Scala, we can just declare it in one line, like customer ID. Inside there is ID. This is our value class, and we can put some additional methods here. I won't go into the details, but you know what I mean. And what bugs can we prevent by it? Mostly bugs of this type. We have a method with two parameters, and apparently both of them are double, right? And we can flip the arguments. Of course, our test will detect that, but again, this feedback loop can be too long for it. Okay, and so at the our stronghold boundary, we parse ID, and then we only use statically typed IDs. So again, it's quite possible in Java to do this, but you need much more code, and in fact your code starts to become less readable, not more. In Scala you can do even better with some implicit classes. This is maybe not so important, but you can even plug some additional methods into your customer ID class. What it does, it takes a string, and here by some magic behind the scenes, this string is converted to customer ID, and we can invoke the method on it. Sometimes it can be kind of dangerous, but I think it also, when used properly, it can make your code more readable. Okay, so that was simple examples. That, wow, maybe it's not really true that we can avoid such exceptions, but if we mix our identifiers, then I think that it is so, right? that value classes and tag types can save us from these exceptions. And then, yeah, this is I guess it's the most common example of avoiding bugs, but by static typing. For those of you who know Scala, I guess it's, yeah, you use it daily. But for those of you who do not, I just quickly skip. So this is option. This is a box for some element, some generic element. Something can be inside or not. And what makes it special is that it has some combinators that allow you to apply functions to what's inside the box without trying to check if there's something inside or not. Because inside there could be null. Right? And if you really want to unpack it, then you can provide default value and get the result which is inside. Or if you are really want to have a risk, you can have a get and the risk exception when there's nothing inside. And these are the ways we can construct it, and unfortunately Scala doesn't protect us from certain kinds of bugs. Like normally you create an option by passing either string or null, and you get empty option or option that's with something inside. Like here you create, these two lines are more or less the same, but you can do this, and inside your option you still have null, which is not so nice, but Scala and Java interoperability forces us to do this. And what's special in Scala is that it has some syntax sugar that make you want to do this. This is how you do it in Scala, like 2 lines, you map your option with some function. And in Java, also there is optional class from, I guess, Guava, but it looks like this. My creation is more or less good, but then, yeah, this is the same code. See how many lines do we have? And in fact, it's not more readable. I would say it's less readable. Of course, with Java 8, this would be much shorter, but I hope you get the point. And so in Java, well, this is usually what you do, right? Because in fact, it's kind of, for me, it's more readable than the code on the previous slide. So syntax sugar, in my opinion, is kind of important in many places. Right, so we're up with these and these exceptions. Now we come to some more elaborate examples. And the fifth one is validation. This is the definition of validation by one of the Scala authors. I don't want to read it. I hope that you understand what it means. Well, I don't, but it's not so bad as it seems, right? We know it's applicative factor and partially applied disjoint union type, but we'll cope with it. But I have to warn you that we'll use Scala's library. This is the quote from guys from Zero Turnaround. So these are not medical Java developers. These are really smart guys. And this is their opinion on Scala Z. So be warned, but validation is the part that's considered, I think, the most sane part of this library. Okay, so how do we do validation? We have our case class person containing two fields named share name. We construct it, but probably we don't want to have nulls or empty fields here. This is another way of saying this. Again, it's kind of Scala syntax sugar. We apply some static function to the person class, and we get a person. And validation in Scala Z looks like this. First, we have a value, and we wrap it with, as an option. We wrap it into a package that says this is result of validation. It can contain success of type string, or it can contain error of some type, right? So this is again some strictly applied method to string that do some implicit magic conversions. Yeah, and name is success, share name will be failure. Again, we have some factor method, and this is our error code. So both of these values are of type validation. One is success, one is failure. So this is this joint type, right? You can have either success or either failure. And what's nice is that we can compose it. Again, this is I know that each sign is heavily overloaded in Scala Z code, but well, so it is. We take one validation, another validation, and we apply it to the function. This is the part that's this applicative functor. I won't go into the details, but as a result, we get a validation. And the validation result, in case of success, is person. Is the application of these two arguments to this constructor. And in case of failure, it's string. In fact, it's concatenation of failures from those two strings. So again, in some cases it's really nice if you have, well, I would say elaborate enough definition of validation to have the validation result that is, well, kind of first-class citizens. It's an object and not validation exception. So that was constraint violation exception that we don't want to catch somewhere high above. And we go to I/O. This is how you usually deal with I/O. You have many cables, you cut one, and you hope it's okay, that it won't throw you an I/O exception. And, you know, in most of the parts of the code, it's okay. But the people who think that throwing exceptions in some places is not so good, because they are invisible in the source code and create many exit points. And this is, I would say, hardcore view that it's better to, you know, return from each function some kind of integer or other types of error values. But it's by Joe Spolsky who founded Stack Overflow. So again, he's not some medical Java developer. So this view is kind of interesting, but still in Java we won't do this, because returning error codes from each function would be a really nightmare and verbose technique. So some hardcore Scala Z, I would say Haskellers, developed other I would say attitude, and again it involves creating some, I would say, packages or boxes called I/O. And what is I/O of string? It's an object that can contain the result of string of type string, but it can throw some IO exception if you try to see what is the string inside. So again, there are some factory methods and some additional syntax sugar that allows us to compose those objects. Well, for those of you who are functional enough, of course, it's an good example of a monad. But I think we don't want to go inside such details here. And again, what do we do here? We construct our package with some string. Again, we take the file name from it. We read some file. We read the line, and then we end up with what's inside the file, right? With some package that can contain string. And in our stronghold, we perform this method just at the end, unsafe perform IO. This can throw exception on us, but here it won't, right? So this is the place. Here we should be free from IO exception according to this attitude, but just below the main and servlet, something like that, we perform the IO. Unfortunately, this technique is kind of difficult to extend if we have more than one package. Like we can have IO and here some state monad or some logging or access to DB. But if we start to think about it, how to mix this stuff, well, it turns out it's kind of you end up with monad transformers that you probably don't want to use. So I'd say that these techniques are just for really important part of the program that you really have to want to be sure about it. But anyway, this is some kind of method to deal with IO exceptions. And now the only exception that is left is array out of bounds exception. This is a bit more tricky because it involves dependent types. How many of you know what dependent types are? Yeah, good. Somebody knows. The place where you may have heard about them is more like in academia than in normal programmer's life. But they are approaching our commercial applications, I think, quite rapidly. So what's it all about? Normally we have a list, and it can have some type parameter, and this is a type. But imagine that we can have a variable or value list of size 5 with length encoded, and here we would have some expression, right? So the type of this list would be a list containing strings having length 5. Yeah, of course in Java and Scala can't do this, right? This has to be type and not expression, not some term. And then we would be able, for example, to write such function for summing two elements of list. Imagine that A is some natural numbers, and we write sum function, and the concatenation returns us a list with size of first list and plus size of another list. Now, this is what I would call a statically defined contract, right? Because normally you encode it with some annotations, JEEConf contracts, and stuff like that, or you just write tests. And here, in the types, we know that the list that will be returned is what size is it? So, yeah, I would say this is the dream. And in large parts, yeah, it is. You cannot do such thing in Scala or in Java or whatever, at least not yet. But there are some ways to come closer. First approach is approximation is to use dependent types from Scala. And what includes it? What does it mean? It means that we can define a class, like family, and inside we define, looks like inner class, right? inside family we have base class child. And then we have a method, like child, children can work, right? Right. And yeah, this is the core. And the method ends. So what's interesting is how we're going to use it. First is one family name, another family name, these are Polish popular names, and then we define a child. A child from family of Kowalski, his name is Pavel, and another child from different family. And we want to invoke method, plural. And you know what? It won't compile, because the type of this variable encodes the fact that it's from this family, from Novakovic family and not Kowalski. So again, under the hood, there's some Scala magic going inside. But this is normal Scala, it just works. Of course, it's still really far away from what we want to achieve, but it's quite remarkable. But now we are coming to different library, and yeah, from now on I'll start talking about really experimental things that probably you won't use in your normal programming day. And we want to define such type. Sec, if you don't know Scala, you can think about sec as some kind of list. So we want to define sized type. That takes two parameters, we don't know what's inside, and the first will be some kind of list, and n will be the length. But in fact, what is n? Because, as I said, we cannot just put some numeric literal, because it won't compile. So, first we'll define natural numbers, and it will be a trait, it's like in Scala. And first we'll define 0, this class or object. I guess maybe it should be object, but it will also suffice. So natural numbers are 0 and successor of some natural number. Does this remind you of something? For me, it's like, you know, going back to high school and learning about construction of natural numbers by PM. And this is so. But it turns out it's more or less sufficient. If you peep into the Scala code, this shapeless code, you'll see more or less this definition with some additional technicalities. So this is how we encode to. This underscore is to avoid overloading with normal longs. This is it, successor of 0. So we have distinct types for each natural numbers. Of course, we need some additional syntactic sugar to make this work, but this is mostly the idea. And then we want define the sized type by hand, but we just will take the shapeless definition. And the idea is that this is the type constructor. It takes variable number of arguments, so we pass Maciek and Próchniak two elements. And what we get inside is this sized object of sized type with some type parameter like contains strings and with the length. This is the type. So this is our approximation. We kind of successfully, more or less, encoded the size of the list by using this technique. Right? Of course, we still have only natural numbers, not integers. To make integers, you have to, you know, go do piano construction, construct some, yeah, just like in school. But still, even with this, we can define such method, right? We take one sized list of size m, another sized list of size m, and then we zip them together, right? We get from that a list of pairs like a, b, the same size. And this is our construct. Please note that the definition of the function says that both of the lists have to have the same size. So again, by using such type, we preclude invoking this method, for example, with one list of having like a length of 10 and another with length of 5. So this is kind of, for me, it's kind of achievement. Of course, it's not so easy to use it still, but this is kind of beginning. And now comes the difficult part. I know you are waiting for lunch, but please bear with me for a few more minutes. Is that we want to have methods that have some more elaborate contracts, like this. This method definition says that this function will compile only if the number n, that's our natural number, will support this condition. And how do we encode this condition? What could it be? Well, again, it's trait, as I said, with all traits and with all things in Scala. So this will encode our condition that we want to impose on this method. What do I mean by that? It means that this function will compile only if the compiler can find an object. This function will compile, invocation will compile on a list of given length only if the compiler, for the length of the function of the list, can find an object of type O of n for that specific n. And for a condition that is always true, it's quite easy to construct such condition. So first we say that, again, implicit is saying to Scala compiler that, if you import some certain scope, then just assume that this object exists, more or less. And so we say that this object is our witness that 0 belongs to our is okay with our condition. And then for each witness of the fact that n supports our condition, we declare that also successor of n also declares our condition. Maybe it's kind of easier if I show you the code for some non-trivial condition. Like, we want to define a function, even fun, that can be invoked only for lists of even length. So how do we do it? We define a predicate that's even. We say that 0, list of length 0 are even, are okay. And if we have n that is even, then successor of n is also even. And this is the place where we say that we want all invocations to contain even number of arguments. So this will compile. But this won't. It says, I cannot find a proof that 3, that's length of the list, is even. So I was quite amazed by that. Still, there's a problem that everything is constant and hard-coded here, but parsing lists will become part of our parsing logic. It's like parsing strings to integers. So this is the encoding of some predicates, and our ultimate challenge, that's the last piece of code that I'll show you today. But it won't be so easy. Is have a function that will compile, a 2-argument function that will compile only if the sum that will have 2 arguments. One of them will be list, but of particular type, and the other will be some kind of our natural number. And this invocation will compile only if the sum of elements of this list is equal to the second argument. Right, so this will compile, but this won't. This is our final goal. In fact, this is the example that I found on some user group. In fact, the original example is far more elaborate because it involves computing some crazy checksums on this list. But I think this will be enough. And again, we proceed just like with our even predicate. We define the trait sum, and we say that there exists an object of type sum with age for list and given natural number only when, well, the sum of elements is equal to 12. Now, this is kind of a special list. It's heterogeneous list that's part of Shapeless, and more or less it encodes in its type, it encodes its types of its elements, right? So that we know that we have a type for number 8, we have a type for number 4, and then this information will be encoded in the type of this object. So this would be the definition of our method. But how do we define the sum trait? So at first we state that empty list, HNL is constructor of, or a constant for empty list, has sum of elements equal to 0. Yeah, that's kind of easy. That's our base condition. And then what do? Well, we proceed by induction. And this is our induction step. Now, this is not so easy to grasp, but it reads like this. I promise this is the last code that I'll show you today, so bear with me for the last time. So it says like this. If we have natural number h and a list t and a natural number partial sum and number sum, and if we know that the sum of this list is equal to this partial sum, right? This is our witness. And we know that h plus this value, this partial sum, is equal to s, then we assume that this list that is created by concatenation h and this t has sum of elements s. When you think about it long enough, it actually makes sense. And this is just, you know, if you had Prolog classes in your CS courses, then it's just like you would do it in Prolog. But here, the Prolog came down to our normal commercial programming language. So, of course, well, probably you won't write it in your application code, but I think that this technique has future, right? So this is kind of verbose, but it really works. Since we're running out of time, I won't show you the code, but I will put it on the GitHub. It's really so that this will compile and this won't. Okay, so just to wrap up, this technique assumes that here we'll do some encoding of our normal, normal lists, to the H list that contain more type information, just like we have parsing arguments from HTTP requests, right? In HTTP requests, we have just strings, and then we have the parsing that converts the strings to some DTOs, to long values, to dates, and so on. So it's this parsing gives us more type information. And here we have to make some additional parsing step, so to have even more type information. So this would be the heavy part. Okay, so that's mostly the end. We got rid of all the exceptions, probably and hopefully. But we have also other benefits. The first benefit is that with enough type system information, our code starts to look like a puzzle. I remember a moment of enlightenment when I wrote some kind of difficult code to make some type-safe queries to some NoSQL databases, and I struggled for quite a few hours to make it even compile. But because it was, well, the types involved were quite elaborate, but finally when I made it compile, it turned out that all my tests passes, right? So with enough type information, just the fact that the code compiles means that it's okay. The compiler can more or less prove that we are right. And when we write the code, it's like puzzles. This is one type, this is another type, and they just fit together, or won't, or don't fit together. And it's not always the case, but when it happens, it's really nice. And also, having enough type information means that we have the best documentation of our code or library that you can imagine, right? I remember like my first encounter with Ruby when I had to do some crazy monkey patching because the author of the library I wanted to use just forgot to put any documentation, any examples, so I would have to, to look through the source code to know what argument does this method need. And here all the contracts are there. You don't have to download documentation. You don't have to download tests to know what to do. Okay, so if we do all this, we can lie and baked pigeons will just jump into our mouth, right? And yeah, I'll end up with not so optimistic view because do this such things. I also don't. I mean, I use the techniques from the first part of my talk, but not the last one. And why is that? Well, there are several reasons. One is still kind of poor IDE support. Like IntelliJ is great, but it's still quite often it doesn't warn you that something won't compile. And another thing is that the libraries I've told you about, Scalaz and especially Shapeless, are still not mature enough. They're still kind of difficult to use, and it feels like doing some crazy scientific experiments sometimes. And the code, as we've seen, is still quite verbose, right? This last example is summed list is well, I would say it's not more readable, but less than if you would do it in normal at least Scala code. So the question is it worth it? Well, I think that for many applications, it's not worth it. Because when you think about what our applications do, then most of them are business applications. They are not meant to be reusable. They're not meant to be reusable. Like when you write some controller, then probably you write the code there with some maybe types, but nobody else would use it. So writing some elaborate contracts, it's kind of not worth it. Like it's enough to have tests, because if somebody wants to change the code, then okay, we'll change the tests or maybe or at least run them. But if you have, if you write libraries more and more generic up to the standard library, then having good type contracts become more and more important. So I think this is the case that the generic libraries like collections, like all kinds of utils, will have to include more and more type informations to make them more usable and more safe to use. Right? And because it's easy to write contracts when you have when your logic is logical, right? When you have some certain contracts and certain laws. But most of our code, at least my code, is not. Yeah, that's more or less last slide. Because my logic usually is not logical. It's just a bunch of ifs thrown at me by some crazy salespersons who just have to keep their KPIs, and making some sane contracts is really difficult. So the last thing that I want to show is some kind of technology radar, just like ThoughtWorks do it. So I think that value classes, options, equals, these are the things that you should use in your code daily. Validation, IO moment, and Scala, probably somewhere in kind of most critical parts of your code. And dependent types are kind of really interesting stuff, but probably not when you have a hard deadline. Okay, thanks, and yeah, I'll probably put the code on GitHub.
Thank you very much.